Finding the orthocenter of the triangle. The orthocenter is the intersection point of all of three altitudes for the triangle. So the altitude is the line that comes from a vertex and runs perpendicular to the opposite side. Think of it as a measurement for the height of the triangle. There are three types of triangles in relation to the angle measurements, and what type of triangle you're dealing with will dictate where the location of the orthocenter is. So if we're looking at an acute triangle where all three angles are less than 90 degrees, when we insert our altitudes, or again, a length that will represent the height of the triangle depending on your perspective, we see that the location of the orthocenter is on the interior of the triangle. When we're looking at a right triangle, you can see that the legs actually represent the altitudes, again, depending on your perspective. So in this case, the orthocenter is going to be on the triangle, right at the corner where the right angle is located. For the obtuse triangle, where one angle is greater than 90 degrees, in this case, we're going to have to extend out these sides to show how we would measure the height if one of these sides that form the obtuse angle were to represent the base of our triangle. Because now when we come from a vertex, we would have to run perpendicular to this extended line to measure the height. Now, the location of all three of these at the intersection point, we'll have to extend these out so that our orthocenter is clearly on the exterior of our triangle. So again, depending on what type of triangle you're dealing with, when we talk about angle measurements in a triangle, that will dictate the location of the orthocenter. So something to keep in the back of your mind when you're looking at a picture to check your work, to make sure that the orthocenter is in the correct location in relation to what type of triangle you're working with. So let's jump over to an example, because that's the best way to illustrate a problem like this. But our goal in general is to find the equations of the altitudes and then determine where they intersect. So we have these 3 points, A, B, and C. We can do a rough sketch of where these would be located on the coordinate plane to get an idea what type of triangle we're working with. So if we have 4, -3, and this won't be perfect just due to the scaling of my own coordinate plane that I'm drawing by hand. So 8, 5, and then 8, -8. So we have A, we have B, we have C. Now this looks like it could be obtuse, but it could be acute. Again, we're not entirely sure, because again, my scaling could be poor. That should run right through that point. So again, we want to write the equations of the altitude. So because all three altitudes intersect at the same point, I only need to find the equations of 2 of them. Now, just to make this thing a little more difficult, let's find the equations of the altitudes that are not this vertical line. So I could easily find the equation of this vertical line right off the bat and say that this is x is equal to 8. Okay, so that's the equation of or that line. And because that's vertical, the altitude that would run perpendicular to that must be a horizontal line, and that would be the altitude that extends from A. So if I know BC is a vertical line, and I know that because B and C share the same x-coordinate, the altitude coming from A must be horizontal, and therefore finding the equation of that line would just be y equals, in this case, the -3. Where's that -3 coming from? That's the y-coordinate from my A, and it extends from A. So that's a pretty easy equation to find, but let's look at the other two to get an idea of how you would calculate the equations of the lines where it's not just a horizontal or vertical line that you're dealing with and requires a little bit more work. So as a refresher, to write an equation of a line, we need 2 things. We need a point that the line passes through, or a point on the line, and then a slope of the line. And once we find those 2 things, we can use our point slope form. So we'll just write that off on the side. Let's first find the altitude coming from C. So if the altitude is extending from C, well then the point C is the point that that altitude passes through, or that is the point on the line that we are going to use when we're going to write the equation for it. So the point that we're going to use for altitude C, we'll say altitude from C, the point is equal to C. Now we also need a slope. So how do we get the slope? Well, we know that the altitude from C should run perpendicular to side AB, even if that has to be extended. So therefore, because I have the points for AB, I can find the slope of AB and then find the slope that should run perpendicular to that, which would represent the slope of the altitude from C. So we're going to want to find the slope for AC first. So let's do it down below, we'll say, or AB, sorry. Slope for AB, we're just going to do change in y, so 5 minus a negative 3 over a change in x, which is 8 minus 4. And we're going to get 8 over 4, which is 2. Now that's the slope of side AB, so the slope that runs perpendicular to it is negative 1/2. And now I have the two pieces of information to write the altitude from C. That's going to be y minus the y coordinate, so minus the negative 8 equals plus 8, negative 1/2, x minus 8. Now, because we're ultimately going to have two equations that we're going to want to find an x and y coordinate from, we're actually going to want to put this in y equals or a slope-intercept form so that we can easily solve the system that results from finding the two altitudes that we want to work with. So let's just do that now. We're going to solve for y. And again, you'll see why this is important after. Distribute that negative 1/2. We're going to get plus 4 and then subtract the 8. So we're going to get y equals negative 1/2 x minus 4. So this is the equation of the altitude from C. Now, let's find the equation of the altitude from B. So we have the altitude from A, y equals negative 3. Now let's do from C. So we'll do altitude from B. So what is the point that we're going to use? Well, it's going to be the vertex where the altitude originates. So it's going to be point B. Now, we know that the altitude from B should run perpendicular to side AC. So we can calculate the slope of side AC because we have the points for A and C, and then just take the negative reciprocal to get the slope of our altitude. So for the slope, we don't know yet, so we'll just do slope of AC. So change in y is going to be negative 8 minus a negative 3, so plus 3, over 8 minus 4. And we're going to get negative 5 over 4, so the slope of the perpendicular line would be 4/5, positive 4/5. So now we have the information we need to write the equation of this altitude. It's going to be y minus the y coordinate of the point it passes through equals the slope x minus the x coordinate. Now we have the equation of the altitude in point slope form. Let's put it in slope intercept form. So we're going to get negative 32 over 5. And if we add 5 here, adding 5 will be 25 over 5, so negative 7/5. So there's that equation. So now, again, we were gifted some coordinates where one of the sides was vertical, or if it was horizontal, that makes it easy to find one of the altitudes because the altitude's either horizontal if one of the sides is vertical, or it would be vertical if one of the sides was horizontal. So, but I want to illustrate a case where we don't have vertical or horizontal sides. We're going to have to go through this process of actually finding the full equation using a point and a slope. So we have these two equations here. Now they're both in y equals format. So by transitive property that we've discussed, if they both equal y, they should be equal to each other. So I can say negative 1/2 x minus 4 should equal 4/5 x minus 7/5. So we're just solving this system using this equation and this equation. We're now going to solve for x. So if I add 1/2 and add 7/5, so we're going to have 7/5 minus 4 equals 4/5 x plus 1/2 x. So here we're going to have negative 13 over 5 equals, and then if we put these both over 10, so we'll have 8 over 10 and 5 over 10 for a total of 13 over 10. We'll multiply by the reciprocal, and we'll get x equals negative 2, because we have to multiply both sides by 10 over 13 to isolate x. And these 13s will cancel. We'll have negative 10 over 5, which is negative 2. So the x-coordinate for our orthocenter is at negative 2. The y-coordinate, how do we find it? Well, we already know that it's going to be at negative 3 based on the equation of that other altitude that we found originally. But let's say we didn't have that information. We can take this negative 2 and plug it back into one of the two equations from the system that you use to find that value. So we can say y equals negative 1/2 times negative 2 minus 4. So multiplying these two together, we'll get a positive 1 minus 4, and that's where that negative 3 comes from, which is what we'd expect. So the location of the orthocenter is at negative 2, negative 3. So in summary, the approach, and we can even check where that would be. So negative 2, negative 3 would be somewhere over here. And if we extend that out, and it looks like this was an obtuse because we're going to have to extend this, extend that. We can see that these things would all intersect. So that looks like, despite the scaling issues that I may have from a hand-drawn picture, that looks like it would be in the correct location based on the location of the 3 points that were given at the start of the problem. But again, in summation, the idea is write the equation of two of the three altitudes, put it in slope-intercept form, and then because both equations are equal to y, they must be equal to each other. And then you can solve for the x-coordinate. Once you find the x-coordinate, you substitute back in. So you're solving a system of two equations and two variables. And we're going to use that substitution method, or you can think of it as the transitive property, which we've been using in proofs earlier in the year. And then once you have, again, that x and that y, there is the location of your orthocenter. You don't need to write the equation of the third altitude because all three intersect at the same point.